Hello everybody, and welcome back to another video on my channel. Today we will be covering our introduction to integration, which is the second other really important thing in calculus after differentiation. Now, as you know, this is actually not the first video of my integration series or my integral calculus series, due to the fact that I was covering Riemann sums before this. And the reason I was covering Riemann sums before this was because I wanted to make sure that you knew the premises behind integration and finding area under a curve before I show you the exact method that's actually used to find this area under a curve. So without any further ado, let's move on to the video. As I said in the introduction, integration is the second other very important part of calculus as a whole, including differentiation being the other part. Now, integration and differentiation are actually opposites of each other. So, if I integrate, and I'll show you the symbols for integrate earlier, but let's say I'll integrate the derivative of a function, then this is just the function. And this is what I mean by opposites. Just like if I subtract 1, then I add 1 to x, then the result will still be x with no difference made whatsoever. Now that that premise is covered, let's move on to continuing other forms and explaining more of what this actually is. It's been explained earlier that integration is the opposite of differentiation, but what exactly is it? And this is where the Riemann sums come in handy. Integration is basically finding the area under a curve. And now we have it written over here, and this is exactly what the Riemann sums did, but instead of finding the exact area, unless in very specific cases, they would approximate the area. So integration, in reality, is just the exact method used to calculate the area under the curve, with Riemann sums just being simple approximations. Now, there are two main types of integration: definite and indefinite. But before we get to that, let's talk about how we actually represent integration. We represent integration with a symbol which kind of looks like a crowbar or a really weirdly stretched out S symbol. This is the integration symbol, and oftentimes when we are integrating with respect to a variable, which always happens actually, so what we do is we do d and then the variable. So if we're doing x, then we have x over here. If it's a function of x, we'd have integral of f of x dx. A function of y, we would have f of y dx, etc., etc. Then, this is not the only thing. Then, what also needs to be explained is that there is also an integration constant and bounds, but that's gonna come when we explain the difference between definite and indefinite integration. And this difference is actually quite simple. Over here, I've drawn a chart, a quick chart, table chart, to compare indefinite and definite integration. And what happens over here is this. Indefinite integration, what it's over here is indefinite integration has no upper or lower bounds, while definite integration does have upper and lower bounds, because what happens over here is indefinite, you're calculating over a certain interval, and in indefinite, you're not calculating over any interval, you're just calculating in general. And now that we know that, the next thing is indefinite integrals will have a constant c at the end. The reason for that is because, let's say we're differentiating d by dx of x squared plus 5. Since 5 is a constant, or c, and the derivative of a constant is 0, we will just get 2x for this, where the derivative of 5 becomes 0. That's why when we're doing indefinite integration or finding the interval over any general area, we re-add that constant c back into the equation to account for the fact that it was removed by the derivative. Now it could just be the base function, like if we integrated 2x, it could just be x squared, but then c would be 0, so that still wouldn't matter anyways. And what about for all the other cases also has to be considered. That's why it's always added back. But for the definite integral, since we're calculating over a certain area, the c's will cancel out. Any additional area will be gained/lost again, or cancel out for or accounted for when we're calculating this definite integral. So no constant c. Now since it's over a certain interval, definite integrals have a value or a constant for an answer, while the indefinite integrals have a function as an answer. So that basically covers the key differences between indefinite and definite integrals, and this also explains just the very basics of what integration means. But we're not done. What also needs to be done is we need to know how do we express this. Now in this video, I'll give you the limit definition of a definite integral, as it only uses knowledge that we already know, and from finding the limit definition for an indefinite integral is way more tricky and might not even be there based on any of the research or any of my prior knowledge that I've conducted. So let's show you the limit definition of a definite integral. Over here we have the definition or the limit version of the definition of our limit definition of the function, or evaluating the definite integral of a function from a to b, where n is the number of subintervals. And if you look over here, this might seem oddly familiar to a formula that was covered in a previous video, and this is pretty much precisely just the Riemann sum formula, or the very basic rectangular Riemann sum formula, but we just take the limit as the number of subintervals approach infinity. And the reason for that is, if we have a graph over here, and if we draw a function, then we draw, let's say, two rectangles. Let's say this is A and this is B. So if we draw here, it would be pretty inaccurate if we drew the rectangles. That would be missing a lot of area. But if we drew more and more and more rectangles, thus that the width of the rectangle pretty much becomes 0, but there are so many, it tends to average out everything and creates pretty much one, and the area is pretty much equivalent to one rectangle, where the area over is also equal to the area it misses. And that's basically one of the special features of this Riemann sum integration, is that basically it averages everything out, and that's how the definite integral is created. Now one quick thing to mention, over here from a to b, this is just showing the integral from a to b, if I didn't explain that earlier. So yeah, I guess that's about it. Thank you so much for watching the video, and I hope you really enjoyed it. If you found anything you want to suggest, please make sure to write down in the comments so I can improve my channel for all of you. And if you found my content educational, inspiring, or enjoyable, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. Thank you so much. See you in the next one, and bye-bye.